All right, here's part D. So we thought we needed exactly 4 divisors, right?
Yeah.
Oops. Thought we needed exactly 4 divisors. And we knew if we have a number like 10
For example.
in the example, 1 and 10 and 2 and 5, we had prime to the 1, prime 1 to the 1, which is 2. Actually, by the way, I don't need to do it abstractly. 2 to the 1 times 5 to the 1. I have 2 choices for each one of these powers to use. I can use 0 or 1 as the power of 0 or 1 with my 5s and with my 2s. Okay, so 5 to the 0 times 2 to the 0 is 1. 5 to the 1 times 2 to the 0 is
5.
5.
2.
5 to the 0 times 2 to the 1,
2.
2.
And then 10.
10. So I have this little rectangular box, and that gives me 4.
Right.
4 divisors, right? So I add 1 to this power, I add 1 to this power, multiply those together, 2 times 2, and I get
You get 4.
4. Okay? But we want exactly 4 divisors,
Yeah.
right? So it has to come somehow. I can either have, when I multiply together to get 4, I can either have a 1 times a 4 or a 2 times a 2.
But one of these 2's doesn't really count.
Well, I'm not making a factor tree, I'm making the ways you can get 4. So that 2 does count,
Yeah.
okay? So why don't we... Here I had 2 times 2. 2 choices times 2 choices, okay? And that was prime to the 1 times a different prime to the 1. But there is another way to get 4.
We can
prime cubed.
prime cube.
When we have a prime cubed, like 8, which is 2 cubed, here I have 4 choices for what I can use for 2. And what does this 1 represent?
1 represent.
Well, that's the 2 to the 0 choice.
Well, I'm multiplying this.
Well, you can't. Well, it's 2 cubed, so there's no other primes in it. So the 1 represents the primes you can't use.
Right, this would be like, this is really 2 cubed times 3 to the 0.
Yeah.
Times 5 to the 0.
Times.
Right? See, I only have 1 choice for all these other ones. Here I only have 1 prime. So this 1 doesn't represent the 2 to the 0. I have 2 to the 0, 2 to the 1, 2 squared, and 2 cubed. And I only have 1 column, 1 times 4. And I only have 1 column because all the other primes had no powers.
Yeah.
Okay, and the factors of 8 are 1,
8,
2,
4, and then
4,
8.
and 8.
8. Cool.
Okay, and so here's the interesting thing. There's only 2 ways to get 4 when you multiply the primes out like this.
Yeah.
Okay, when you multiply those powers. The first one we found was the 2 times 2. The second one we found with the cubes is 1 times 4.
Yeah.
So, Dave was wondering how to describe all these numbers with this property. Can you describe some of them, please?
Well,
we have 2 sets of them. What's one set?
if we have our number x, we can have an example like this, where we have p1 to the 1 times p2 to the 1 times 1.
Okay. Now,
This is for some of them.
that's some of them.
And we can also.
What's the other set? Go ahead.
We can also have primes cubed.
All right, why don't you write that down?
So
Y equals,
y equals like maybe 5.
okay.
Well, abstractly, it would be p cubed.
Yeah, some prime cubed. Now, is there going to be any overlap in these 2 sets? Can prime 1 times prime 2 ever equal some other prime cubed?
Well,
Nope.
no, because in this set we only have 1 prime,
Yeah.
and that's it. You have 2.
And you can
Two
factor,
different primes.
the way you can factor numbers, they factor uniquely into primes.
Yeah.
So there's no overlap. And is there a third group?
No, because there's only 2 ways to make 4.
There's only 2 ways to make 4. High five. Good work this morning, guys. That's a tough problem, but a neat problem. It shows how these simple counting ideas for counting the number of divisors lead to really interesting thoughts about numbers and how they work. Right?
Yeah.
Did you like that?
Yeah.
Yep.
All right. Good job, guys. Good job.